In the name of God. Hello dear professors and audiences, my name is Nima Imani and I'm one of the three authors of the paper with the title Energy Efficient Power Allocation in MIMO-NOMA Systems with Zero Forcing Receiver Beamforming in Multiply Clusters. Due to the excellent performance of MIMO systems in spectral and energy efficiency, these systems have been considered as one of the key technologies in fifth generation. Low complexity in signal processing and high spectral and energy efficiency and reliable communication are the main advantages of massive MIMO systems. Figure 1 investigates the sum rate variation with the transmitted power for MIMO-NOMA and MIMO-OMA. And figure 2 shows how energy efficiency varies as the number of users in each cluster increases in two scenarios with different distances. The modeling of path loss is formulated as follows by considering the surroundings and the distance that the transmitted signal travels between the base station and distributed users in model. For example, figure 3 shows a base station and some users, and all of these circles shows a cluster. The intended channel between the signal transmitting antennas and the distributed users is in the form of a Rayleigh fading, which is obtained as follows in equation 2. Equation 2 shows us a channel matrix that in this equation, M is number of antennas and K is the number of users. The effect of path loss in the channel matrix is applied as equation 3. In equation 3, we can see that the equation 1 that shows the path loss that we calculated in previous slide, in this slide, is multiplied to GAM and K that shows the channel matrix. With this multiplying, we can lead to equation 3 that shows us the effect of path loss on channel. The beamforming in our proposed scheme is considered to be fixed. First, we obtain U by the singular value decomposition of the channel matrix as follows in equation 4. And in this equation, U and Q are unitary matrices and F denotes diagonal matrix of singular values of channel matrix. Then we design the beamforming. The zero forcing beamforming receiver is calculated from the following formula in equation 5. The effect of applying the beamforming and zero forcing receiver in the channel created between the M and K user and the base station is evaluated in equation 6. In this equation, T beamforming is transmit beamforming, which has different values for different clusters. In the MIMO-NOMA scheme under consideration, the signal sent by the base station to the surrounding users is formulated as equation 7. That in equation 7, S is information signal and W is matrix that the base station uses for precoding. And in equation 7, S multiplied to W, and we can evaluate the desired value. The observed signal by considering the channel estimation error in the user M and K is formulated in equation 8, where the noise is additive white Gaussian noise denoted by NAM and K that we can clearly see in equation 8. By affecting the detection vector via MAK on the received signal of the user M and K, we have equation 9. The effective gain of the channel can be assumed in descending order as equation 10. The signal to interference and noise ratio SINR at each user's can be evaluated in equation 11. Hence, the achieved data sum rate is equal to equation 12. Power consumption in the problem of optimization energy efficiency is divided into two main parts, which are the user transmission power and the fixed consumed circuit power. The desired optimization function is formulated as follows in equation 13, where PSC denotes the fixed consumed circuit power. The goal is to maximize energy efficiency. This optimization problem has two constraints. These two constraints include that the rate of each user must have a higher rate than previously defined, and also the total power of users must be less than the maximum transfer power. The optimization problem with this existing constraints is formulated as follows in equation 14, where constraint C1 indicates that the rate per user must be higher than a predefined rate, and constraint C2 states that the total power of users must be less than or equal to the total transfer power. The total transfer power denoted by PA max, and PA max denotes the flexible transmit power. The objective function 14 that we evaluated in previous slides is non-convex and fractional form. Using the Hessian matrix property, the objective function is simplified as follows in equation 15. In equation 15, Q is used to indicate the maximum value of energy efficiency. Using the Rayleigh fading and channel state information, the lower bound of data rate is calculated in equation 16. The main optimization problem of 15 is simplified as follows in equation 17. The relation obtained in equation 17 is a convex optimization problem. Now we have a constraint problem. We need to eliminate the existing constraints. By doing so, we employ the Lagrangian function, which is written as follows in equation 18, where Z indicates the acceptable power for each user, that W should be higher than 0, also indicates the Lagrangian coefficient for the constraints considered for maximum transmission power, which is a coefficient of 0 or positive. Rho M and K must be higher than 0 is also a coefficient of 0 or positive, which is the Lagrangian coefficient corresponding to the minimum rate required per user. The proposed iterative algorithm is shown in equation 19, equation 20, and equation 21. And also, it is clearly shown here. To obtain optimal power of users, we set the derivative of the Lagrangian dual function equation to 0. Using equation 19, the optimal power of user is obtained from the following equation. In equation 20, and in slide 12 and 13, we can clearly see the proposed algorithm of our paper. Table 1 is the list of important parameters used in the simulation processes. Figure 4 represents how the energy efficiency of the system varies by increasing the minimum users, data rate, and 2-user and 3-user scenarios. The distance of users is considered to be 25 meters for both scenarios. The total transmission power is also considered to be P equal to 20 dBm. By increasing the minimum user data rate, the energy efficiency value of the system decreases sharply, such that for the 3-user scenarios of R equal to 7 bits per second per hertz, the energy efficiency reaches to 0. Figure 5 represents the energy efficiency behavior of the system with the increasing of the total transmission power. These scenarios are illustrated for this figure, and the minimum user data rate is 2 bits per second per hertz. Figure 6 shows how the total user data rate varies based on increasing the sigma n to the power of 2. This figure is drawn for 2-user and 3-user scenarios. The difference between the proposed method and the equal power allocation scheme decreases with increasing the sigma n to the power of 2. For instance, in the sigma n to the power of 2 equal to 0.3, the total user data rate for both schemes is equal. Figure 7 shows how to achieve a stable state energy efficiency of the system. This simulation is examined for 3 scenarios. Scenario 1, in scenario 1 we have m equal to 3, in scenario 2 we have m equal to 6, and in scenario 3 we have m equal to 8. In scenario 3, antenna reaches stability after 11 repetitions. In scenario with m equal to 6 antenna after the 4 repetitions, and finally in third scenario that m is equal to 8 antenna after 16 repetitions. These results are based on average value over 50 runs. We have some conclusions in our paper that I want to summarize these conclusions. In this paper, to maximize energy efficiency, we find the right power for each user using an iterative algorithm. The system in equation is a MIMO-NOMA system in the presence of channel error estimation. Some important parameters that affect the channel, such as the pass loss and receiver type, are also considered. Using the Lagrange dual function, an iterative algorithm for the optimal power allocation is proposed to users of the systems. As proved in the simulation results, the proposed algorithm to solve the proposed power allocation problem has better numerical results than other methods. Finally, I want to thank you that listening and watching this presentation. And if you have any question and if you have any problem, you can email me and I will respond you as soon as possible.